Hello, my name is Conor Hennessy. I'm a research assistant with the Evans Policy Analysis and Research Group at the University of Washington. And this is submission number 86 to the Data for Policy 2021 conference, New Methods and Novel Data for Estimating Seasonal Hunger. So a little bit of background about food insecurity and seasonal hunger. Food insecurity is oftentimes seasonal, so it changes quite a bit throughout the year because where consumption smoothing technology doesn't exist, it doesn't in a lot of parts of the developing world. Food insecurity depends on agricultural output, which of course depends on the season. So one issue this creates for researchers is that data, does not exist frequently throughout the year. Data points are often taken years apart, and this makes it quite difficult to study anything that happens seasonally. So between any two data points on hunger, a lot has changed. People have come in and out of food insecurity. And this is, this lack of frequent data is a problem for many issues in development research. And one thing that's been happening in recent years is researchers have been using novel data sources like satellite data and cell phone data to conduct research on these when things that need more frequent data. So the advantage of these new and novel data sources is they're more frequently available, sometimes close to real time, and they're oftentimes low cost to obtain and even have global coverage. So there can be, satellite data from a country you would never get survey data from. But the disadvantages of these novel data sources is they don't usually estimate what you're actually interested in. So in this case, like the satellites aren't actually measuring seasonal hunger. But if you have existing survey data on the subject you're interested in, that can be used to train a machine learning model on the novel data source you're using, so satellite data, if some sort of relationship plausibly exists between the data you have and the outcome you're interested in. So in this case, satellites can measure nightlight intensity, which has been demonstrated to correlate with poverty and consumption, even at the monthly level, and also on climate factors, so temperature and precipitation, which have been demonstrated to correlate with agricultural output. And then agriculture and output and poverty both correlate with hunger. So it's plausible here that this satellite data could be used to estimate seasonal hunger. So the goal of this paper is to take data from satellites, data on climate factors and nightlight intensity. And we specifically for this paper stuck to data that's publicly available for free and has global coverage, and use those data in conjunction with survey data that already exists on seasonal hunger to train a machine learning model to estimate seasonal hunger at the monthly level. So the data we actually have for this is climate data from a database called CHELSA, which has the monthly average daily high and low and average temperatures. And nightlight data from NOAA, the United States National Ocean and Atmospheric Administration, which has nightlight intensity monthly. And these data were pre-processed, the climate data, to show deviations from past averages, as farmers tend to acclimate to whatever temperature and precipitation is typical in their region, but crop yields can be especially affected when the weather is significantly different from that. And then also for each month where hunger is being estimated, the climate data dating back to a year before the most recent harvest is included as independent variables. And then to train this model, we have data from the LSMS ESA survey in Malawi from 2012 and 13, when people were asked, households were each asked, did anyone in your family not have enough to eat in a certain month? So we have data on each month from 2012 through 2013 on whether or not households were running out of food. And we aggregated this at the enumeration area level, which is enumeration area is the smallest level of aggregation. In the LSMS ESA surveys, it's roughly one village. So then evaluating this model is a little bit tricky because there is a relationship between these satellite, the climate and nightlight data and seasonal hunger. But so how good is that relationship is sort of a difficult question to answer. So we compare a regression we run with these data to a regression we run using only past hunger data, which we sort of presume to be what the current level of knowledge is, or a proxy for the current level of knowledge amongst stakeholders and development practitioners. And then another model based on crop yields reported in the LSMS ESA surveys, which shows a sort of theoretical ceiling to how well a satellite-based model could work. Because of the large number of independent variables, all of these models I implemented using ridge, lasso, and elastic net regressions, as well as OLS regression. I will only show the results from the OLS regressions because for whatever reason, OLS actually performed better than ridge, lasso, and elastic net in this case. And then typically a random subset of data would be withheld from the training data to test the model. I did not use a random subset in this case. I used 2012 data as training data and 2013 data as testing data. And that's because this model was specifically meant to show, how well estimates could do in sort of years when survey data was not available. So a random subset would, perhaps optimize the model, but whenever a random subset of training data can be withheld, that sort of implies that survey data exists, which makes this model obsolete. And so, as you can see from this table, the model based on satellite data has an R-squared that's significantly higher than a model based solely on past hunger data, which is our proxy for what development practitioners would be working with now. But you see, when the satellite-based model is used to actually make predictions of hunger rates, those predictions tend to be within 10% of the actual hunger rate, a little bit less than the model based on past hunger, and that's especially true if you eliminate months when the hunger rate is 0, of which there's a significant number. So my model is not likely to be the best model of this sort that is possible. It could potentially be improved with more sophisticated projection methods than ordinary least squares regression. And it could be improved by the addition of satellite imagery used to estimate hunger, crop yields, or things like that using convolutional neural networks. I didn't do those things for this paper, although we are working on those lines of research this fall. It wasn't done in time for this conference. But what the high R-squared of the satellite model does show is that this sort of strand of research does have some potential. It is possible to establish a relationship between these satellite factors that are available monthly, publicly, and for the whole world, and seasonal hunger, which is significant. And since this data has global coverage, it might be possible to find seasonal hunger data in countries where there's been no survey data available before, it might be possible to have hunger data at a frequency that's not been possible to before. So as I mentioned, we're continuing to work on this line of research this fall, but that is all for this presentation. Thanks for watching, and I'll be at the conference if anybody has questions.